An important fact is that any signal can be broken into sum of two signals, one of which is even and one of which is odd. To see this, consider the signal even signal of the set of x of t equal to 1 by 2 x of t plus x of minus t, which is referred to the as an even part of x of t, even part of x of t. Similarly, the odd part of x of t, that is even of odd the set of x of t 1 by 2 x of t minus x of minus t. It is simple exercise to check that the even part is in fact even, that the odd part is odd, and that x of t is a sum of two, odd plus even plus odd. Exactly analog definitions hold in the discrete time case. Exactly analog definitions hold in the discrete time case. An example of the even-odd decomposition of a discrete time signal is given in figure 1.18. That is, this is, we can say, x of t. This is x of t. So we can say x of n. Just we are t equal to n. That's all. Then here time also minus. That's why minus. Okay, not here. And then this x is also minus. That's why minus. Here also say x of in this here even signal 1 by 2. Okay, x of t, this is okay, this is x of 1 instead of x of t, x of, that is we can say, okay, x of t, then x of minus, this is t only minus, that's the minus. Okay. Here in odd signal, here x of t, this is the x of t, this is x also minus, okay, t also minus t, so minus x minus t. The simple exercise, check that the even part is in fact even, that odd part is odd, and that x of t is sum of two. X of t is the sum of two. This is of 50%, this is 50% of the two. We exactly unlock definitions hold in a discrete time case. Exactly analog definitions hold discrete time cases. Discrete time cases. An example of the even or decomposition of a discrete time signal is given in 1.18. Exponential and sinusoidal signals. In this section, and the next, we introduce several basic continuous time and discrete time signals. Not only do these signals occur frequently, but they also serve as basic building blocks from which we can construct many other signals. not only do these signals occur frequently, but they also serve as basic building blocks from which we can construct many other signals. Continuous time, continuous time, complex exponential and sinusoidal signals. The continuous time complex exponential signal is of the form x of t equal to c e power at. Okay. C, C and R, sorry, and A are in general complex numbers. C and A, this is the complex number. Depending upon the values of these parameters, depending upon the value of these parameters e power a, the complex exponential can exhibit several different characteristics. Due to these values, that is C and A, C and A, sorry, C and A, not A, C and A, okay, C and A are in general complex numbers. Okay. Depending upon the values of these parameters, the complex exponential can exhibit several different characteristics. Complex exponential can exhibit several different characteristics. Real exponential signals. And as illustrated in figure 1.19, if C and A are real, if C and A are real, C and A are real, in which case x of t is called real exponential. C and A are real, in which case x of t is called real exponential. There are basically two types of behavior. If A is positive, then as t increases, A is positive, bottom point, A is positive, t increases, that is x of t is behaving exponential. A form that is used in describing many different physical processes, including chain reactions in atmospheric atomic explosions and complex chemical reactions. The complex chemical reactions. If A is negative, then x of t is decaying exponential. Decaying exponential. A signal that is also used to describe wide variety of phenomena, including the process of radioactive decay and the response of RC circuits and damned mechanical systems. In particular, as shown in figure problem 2.61, 2.62, the natural response of the circuit figure 1.1 and the automobile in figure 1.2 are decaying exponentials. Also, we know that for A equal to 0, x of t is constant. X of t is constant. A is 0. X of t is constant. Continuous time real exponential x of t ce at cc e power at e c and a only important. If a is greater than 0, then positive side. If a is less than 0, the negative side will grow. Exponential signal. Periodic complex exponential and sinusoidal signals. Periodic complex exponential and sinusoidal signals. Yes, periodic but complex, that one is exponential and sinusoidal signals. Yes, second important class of complex exponential is obtained by constructing a to be purely imaginary, specifically considered. That is, a second important class of complex exponential is obtained by constraining A to be purely imaginary. A third important class of complex exponential is obtained by containing A to be purely imaginary, specifically consider x of t equal to e power j omega t. An important property of the signal is that of is periodic. To verify this, we recall from equation 1.1 that x of t will be periodic with period t. That x of t will be periodic with period t. E power j omega t equal to e power j omega t equal to e power j omega t plus t, that is periodic. This one equation number 1.22. Or since e power j omega naught t equal to e power j omega naught t plus t. Okay, that is p periodic. This one, this is period. T is the small t is the period. That's all. Then here, since e power j omega naught into t plus t, small t plus capital T, that is equal to e power j omega naught t. In power it will be multiplied e power j omega naught t. It follows that for periodicity we must have e power j omega naught t equal to 1. That is, follows periodicity, we must have for following periodicity purpose maintaining like this. If omega naught is 0, then x of t equal to 1. Omega naught is 0, then x of t equal to 1, which is periodic for any value of t. If omega naught equal to 0, x of t equal to 1, which is periodic for any value of t. If omega not equal to 0, then the fundamental period t naught of x of t, that is smallest positive value of t, or which equation 1.23 hold is e power j omega naught t equal to 1. That is smallest positive value of t, which is equal hold is t naught equal to 2 by divided omega naught. Okay, t naught equal to 2 by divided mod omega naught. Thus, the signal e power j omega naught t and e power minus j omega naught t have the same fundamental period. A signal closely related to the periodic complex exponential. A signal closely related to periodic complex exponential is the sinusoidal signal. X of t equal to a cos omega naught t plus phi. X of t equal to a cos into omega naught t plus phi, as illustrated in figure 1.20, with seconds as the units of t, the units of pi, and omega naught are radians and radians per second. Respectively, it is also common to write omega naught equal to 2 pi f naught, where f naught has unit of